I'll call it as square. So internal DAC square, I'll open this. Just give it as DAC. Save. Now LPC 2148 as the controller. Select it. Include the startup.s. Now startup.s, you open it, and one changes what you have to do is PLL setup, you uncheck it and save. Now new program, new file, I'll paste my program. So I have one more for loop to be copied. I'll copy this for loop. Paste it. Now I'll save this. So DAC.c. So it is saved. I have to include this to my source group now. So right click on source group 1, add existing file from the source group DAC C program. I'll add it. Close. After that, target, right click, because there's settings you have to do when you burn this program, when you burn the X file of this program to the microcontroller. All these options needs to be set. Right click on target 1, go to option for the target 1. So 12 megahertz and say use microlib, output, create X file. So go to linker, choose memory layout from the target dialog, say OK. So now it's ready for compiling. I've compiled it, so 0 errors and 0 warnings. I'll say build it. So successfully built, 0 errors and 0 warnings, and X file is also created. Creating X file is also created. Now next, I'll show you first how to simulate this program here itself. In the Keel IDE, it can be simulated. So you have to just first go to the debug. Okay, go to the debugger, and after going to the debugger, okay, now you will not go to the registers to check the output here, or what is that? This is the waveform. What output you get? The waveform. So you can see here this logic analyzer, analysis window. Click here and choose logic analyzer. So this is what logic analyzer you're seeing. Let me drag it little down. So this is what the logic analyzer. Now just go to setup, and here you have to create a variable. So just this is for creating a new variable, and this is for deleting the existing variable. Since there are no variables here, I'll just click here. Now it will ask me to give the name of the variable. You can give anything. I'll just give it as a out, because when you want to analyze the logic, some variable name should be given there. Now I've given it as a out. I'll just say close. So if I click again here, out will be there. Now if I don't want out, I have to give some other name. So you can delete it by clicking here. It's gone. Now I'll create the new, and again I'll name it as out, because that is okay. Analog out. With that meaning, I'm giving it as a out. Why I'm taking it as a out? Because analog output. Okay, close. And it's not mandatory that you have to write it as a out only. Now after doing that setup, you can go to debug and say run. If I say run now, you should get the square wave here. See, square wave. What you're observing is the square wave. If you want, you can stop it also. Stop. Now what value is this? So this is 1023. That is the maximum value, and this is 0 value. The first for loop, how many points it has drawn from here to here? It has drawn 1023 points, and the second for loop, from 1023 all of a sudden it goes to 0, and from here you have drawn 1023 points again, and this is the square wave. So this is one way of running it. You can simulate this here itself, because this is an internal DAC. Now I want to simulate this in the protest simulator. Is it possible? Yes, it is possible. Let me stop debugging this. I'll go to the protest simulator. I've already created one. So protest simulation. So this is internal DAC. I've already created. I'll just open this. So this is the simplest one. one digital oscilloscope you have to add. It's opening still. Yeah, opened. So this is the same circuit which I showed you in the other experiments. It's the same. So LPC 2138, because instead of LPC 2148 you can use LPC 2138 also. And so just observe this. This is the oscilloscope, digital oscilloscope that is connected. Where to find this digital oscilloscope? Here. So if you click here, you'll get, see, digital oscilloscope, logic analyzer, you have DC multimeter, DC voltmeter, everything is there. Now what you have to choose is oscilloscope. I have chosen the oscilloscope, so click there and connect. Now where to connect this? Let me delete because this is not required for me because I've already placed. Where to connect? Now what is our analog out pin? It is P0.25, that is A out, pin number 9. So connect, here the P0.25 and pin number is 9. This is the port pin 0.25 and connected to A. So you have A, B, C, D, 4 channels here. So you can connect it to any of them. If you want A, or I don't want to A, I want to be connected to B, yeah, you connect it, not a problem. You can connect it to any of the channel. Either to A channel or B channel or C channel or D channel, anything is fine. I have connected to A channel. So now we'll go for simulating. This is the only connection, simple connection it is. Next what you have to do is you have to double click on this because I want to load my X file to this. I've already compiled my program and already the X file is created. X file. This is the program which is there on my desktop. I'll just go to this, double click on this. Let me choose my program, X file. I'll just go back to the desktop. Now here I go to search for, I think I gave, internal DAC square. This is the program and this is the X file. Open. Okay. Now I have to say simulate. Now my program is, X program is written to this. Now if I simulate, I have to get the square waveform in the digital oscilloscope. So simulation is running, so you'll get it. Yeah. So this is what the digital oscilloscope. This is what the oscilloscope you are connected. When you run, so this is how it comes. You can see here. This is channel A, channel B, channel C, channel B, channel D. 4 channels it was having, correct? No, A, B, C, D. Now out of these 4 channels we are using only one channel, that is channel A, yellow color. So the waveform is also in yellow color, you can observe. So the square wave is generated and it's generating, continuously generating. So how you can say it is continuously generated? Just observe this, it's keep moving, correct? No, it is moving. That means what the square wave is continuously getting generated. Now and this is a knob where you can adjust the time period, correct? No? Say for example I want to increase the time width. See here, increased. I want to decrease the time width, decreased. And this is for the voltage for the channel A. This is how you can do it. I hope you understood. Let me stop now. Digital oscilloscope. Sometimes if you close the digital, I'll close the digital oscilloscope here and stop the simulation. I run the simulation now. See, simulation is running, but there is no digital oscilloscope displayed. What you have to do is you can just go to the debug. In the debug, the last option is digital oscilloscope, and again this option you'll get only when the simulation is running. So click here, it comes. So if my suggestion is not to close this digital oscilloscope, just to stop the simulation without closing the oscilloscope. Now I'm not closing this, I'll just stop the simulation. It's gone. Now if I run, it will come automatically. See, it came automatically. Now if I close this and if I run the simulation, stop the simulation and run it, I got to get the digital oscilloscope from the debug. Okay, this is what is the square wave generation using the internal DAC. Now let me get back to the presentation. Okay, so here I completed the square wave using square wave generation is using the internal DAC. Next is triangular wave program using internal DAC. So this also I've already explained. 1 second, because some alignment I have to do this. Yeah, and here also, because this conversion has come down, it will confuse you. Yeah. save. Yeah, so same thing, count as 0 and I have value initialized to 0 here, and again pin cell 0 because I want to make P 0.25 again act as the A out. So 18th and the 19th bit should be made as 10, and then count is equal to 0, count less than 1023, count plus plus. So what I'm doing now, so in the previous example, value is equal to 1023 I have to take, and value left shifted by 1023 left shifted by how many times? 6 times. Now what I'm doing now is instead of value, no value, count itself is given here. Count initially 0, 0 left shifted by 6 times, the 0 goes to this position 6 to 15th position, and it enters into the value field of the DACR, and the DAC will go for converting 0 to the analog output. And similarly here, and again count 0 to less than or equal to 1023, count plus plus, DACR is equal to, oh okay, I think I made a mistake here. Yeah, this is triangular waveform, so this is wrong because I have to start it from 1023 and less than, sorry, greater than 0, count minus minus, count minus minus. This is what I have to do. Count should be initialized to, save, count should be initialized to 1023 because in this loop I have counted from 0 to, the waveform is something like this, 0 to 1023. Now I have to decrement from 1023 to 0. Now count is equal to 1023. If the count is greater than 0, count minus minus, count left shifted by 6, assign it to DACR. Now the previous for loop will give the waveform like this, and the next for loop, this for loop, will give the waveform in the reverse direction, opposite direction. So now we'll see the simulation and execution of this in the Protest software again. Now I'll just copy this program. Yeah, triangular waveform, I'll copy this. Now what I'll do is I'll not create a new project now for this. Let me replace this program, same project, I'll put the new program, Control V. So this is the triangular waveform program which I'm putting now. Copy, Control V. Okay. Otherwise, if it confuses, let me copy this entire program, cut, and let me close this project. Close project. No, don't do any changes. Now project, new microvision. Again I'll go to the desktop. So I'm in the desktop. I'll create here one more folder. So I'll give it as internal DAC, triangle. I'll open this. I'll just name it as try. Save. LPC2148, because all these things, let me go fast here. Yes, startup data is included. Here I have to uncheck the PLL setup. Save the program. Now go to new. Let me paste my program. I've already copied it. This is the triangular program. You can see here. Count 0 to 1023, count 1023, count greater than 0. Now I have to save this. So let me, where internal DAC square it is coming. Let me go up. Now triangle, here I have to save. I'll give the program name as try.c. Program is saved. Now I have to add it to the source group. Add it, close. Now program is added. Now target one, I'll right click. So use 12 megahertz, use microlink, go to output, check X file, linker, use memory layout from target dialog. Okay. Next I'll go for compiling. So 0 errors and 1 warning. Okay, warnings can be ignored. Now build it. Creating X file. Yeah, that's fine. It's done now. Now I can simulate as usual as I simulated the square program here only in the Keel IDE, so this can also be simulated here itself. Go to debug first, go to the debugger, yeah, and then after going to the debugger, here logic analyzer, click logic analyzer, expand it, and then go to setup. You have to create a logic analyzer signal or the some variable you have to create. I'll create it as a out, close. Okay, now that is what I've done. Now I'll go for running, go to debug, say run. See, there's the triangular wave which you are seeing. Now you can stop this if you want. Stopped. So this is at the 0. The first for loop, what it will do, from 0 it will start writing how many points, 1 0 2 3. Every time the points, this is moving, it will be moving with respect to the time. So 0 to 1 0 2 3 points in this direction, and in second for loop it will start from 1 0 2 3 and it will start plotting the points downward. So this is how the triangular waveform. Okay, so you understood this, and now let us simulate this in the protest as well. So again, for protest simulation also I use the same thing. Everything is same, only thing is the program I have to change. So double click on this, go to this. Now this was the DAC X which we wrote earlier. Now I have to write this internal DAC triangle. So try X, open. Okay, now if I run the simulation, here it should give you, yeah, I'll just show you, it will come because some fine adjustments you have to do here. Now this is not the one, I think here, yeah, so this one I have to drag it little, yeah, it's coming, it's drawing, you can see here, it's plotting. Since that was happening very fast and this is little slow because this is correct, no, that was happening in single step, 1 0 2 3 at once it was doing, but this is counting from 0 to 1 0 2 3 and then down counting from 1 0 2 3 to 0. That's the reason. See, it's if I drag the cursor here, the scroll bar here, you can see it's plotting and then coming down. You can easily understand. Yeah, here I'll show you. Yeah, so this is down count, this is up count, down count. Now hope you understood with this. So now let me stop the simulation. So the next thing we'll continue with the presentation. Now if you have understood these two programs, generating the square wave using internal DAC, generating the triangular wave using internal DAC, then external generating the square and triangular wave using the external DAC is easy. Now this is what. Now we are understanding the external DAC. The external DAC that is used as DAC 080S. This is the IC number of the external DAC. Now till now you understood the DAC which is there inside the LPC2148. Now we'll understand how to interface the external DAC 0808 to LPC2148. So the external DAC, outside DAC. Now it is an 8-bit DAC. The external DAC which we are using, this DAC 0808 is an 8-bit DAC, whereas the DAC which was there inside LPC2148 was a 10-bit DAC. So the minimum value which you can give here is this. How many zeros are here? 8 zeros. 1 2 3 4 5 6 7 8 zeros in binary. In decimal it is 0 0. These 4 zeros corresponds to this 0 and these 4 zeros corresponds to this 0. And hexadecimal again it is 0x 0 0. And the maximum value which you can give in this 8-bit DAC is all ones, and that is in decimal 255, and in hexadecimal it is 0FF. This you know. So now how the external DAC DAC 0808 looks, it looks like this. See, it has 8 pins here, A1, A2, A3, A4, A5, A6, A7, A8. So because it is an 8-bit DAC, you can give 8-bit digital data to this. 8-bit digital data. Now what it will do, it will give the analog data via pin 4, I out. So this pin 4 gives the analog output, and the rest others are for giving the voltage supply, plus V reference, minus V reference, and then the what is compensation pin, and then VEE pin, to which you apply the minus 15 volt, and this through a capacitor you connect it to minus 15 volt, yeah, and this is plus V reference, to which you apply the plus 10 volt, and this is the minus 10 volt, and this is where you get the output. So analog output. These are the digital input pins, and this is the analog output pin. This is what we connect now to LPC 2148. And these digital pins of DAC 0808, we are going to connect it to the port pins of LPC 2148. Now what port pins we are using? The port pins used in the program is P0.16 to P0.23. So these are the port pins which we are using. Now, and remember, and even when you go to the lab, the same port pins will be used, because there this DAC is connected to port pin 0.6. These pins of this DAC are connected to P0.16 to P0.23, because A1 is connected to this, A2 is connected to P0.17, A3 is connected to P0.18, so A4 is connected to P0.19, and similarly A8 is connected to P0.23. From 16 to 23, how many? 8. 16, 17, 18, 19, 20, 21, 22, 23. 8 pins are there. 8 port pins are used, and these port pins even we are using in the program, and the simulation is also done using the same port pins. Okay, now here this is the square wave program using external DAC. Now this same header file you have to include. So we have unsigned int var here, and a delay, a prototype, function prototype for the user defined function with the name delay. It's not returning anything and not taking any parameter, hence it is void. Next here, in the main, what we are doing, pin cell 0, I'm assigning all 8 zeros. What it is doing, it is making the port pin 0.0 to 0.15 operate in general purpose input output mode. And then here P0.25 is not required, because P0.25 is required only when you are using the internal DAC. Now I'm not using internal DAC, I'm using the external DAC. What DAC? This DAC, and this is the analog output pin is what? 4. Now I don't require P0.25. And then what are the pins which I'm using now in order to connect the digital pins of DAC 0808 to the LPC 2148, P0.16 to P0.31. Now again pin cell 1, everything I mentioned, because P0.16 to P0.31, sorry, this is P0. What pins we are using is P0.16 to P0.23, but assigning 8 zeros to pin cell 1 will make all the port pin from 0.16 to 0.31 to act as general purpose input output pin, but we are interested in only the port pin from 0.16 to 0.23. Next, we got to make P0.16 to P0.31 as what? Output pins. IO0 DIR, because it is the port 0, IO0 DIR FF. Now what this FF data will do, P0.16 to P0.131, it will make it as output pins. And next, IO0 pin 0 I am assigning, and then var is initialized to 0, and then delay. Now this is what I'm doing. So I'm calling a delay. See, for IO0 pin, I'm assigning 000. This is the data assigned, and var is initialized to 0, and then the delay. So now this bits, observe this. The third and the fourth bit from the left. These two bits are 0, 0. So the value that goes to pin 0.6 to 0.31 is 8 zeros. Now this is, here the waveform starts from the 0, because I'm starting from this position. Now you can observe it's continuously moving. You can observe this portion. So waveform is starting from the 0, and with the delay for this much amount of time it will continue at 0, and after that I'm assigning IO0 pin FF. I'm assigning, that means P0.16 to P0.23. earlier it was 000, now I'm making it as FF. P0.16 is 1, P0.17 is 1, like this P0.23 is also 1. Now it will go high, and with the delay it will continue with the high for this amount of delay, like this. So same amount of delay we are using. Now if I say instead of square wave, rectangular waveform, so I have to write 2 delays. So one a bigger delay and one smaller delay, then you'll get a rectangular waveform. Now the delay is same for both, so you are getting it as a square waveform, and this is repeated. So this is the square wave program using external DAC. The program is simple, and this program I cannot simulate it in this keel. So this program cannot be simulated in the Keel IDE because this requires an external DAC. So the earlier two programs I was able to simulate in the Keel because the DAC which was used was an internal DAC. So now since the DAC is external, this program cannot be simulated in the Keel IDE. Now I can compile my program, I can get the X file, and the X file should be transferred to the microcontroller, which is LPC2148 interfaced with DAC 0808. So that is what we will do now. Let me do that. I'll copy my program. So this is the program. I'll copy this. I'll go to Keel. So let me stop this. It's still running. And open the new project. Close this project. Close the project. Open new microvision project. The folder. I'll create a new folder for this. New folder. Now earlier I used to name the folder as internal DAC. Now I'll say external DAC square, because first what you're seeing is square program. Square. External DAC square. External DAC square. Now here SQR let me give, that is enough. Save. Controller LPC 2148. Choose the controller. Create the startup.s. And startup.s configuration wizard, uncheck this.